Hello, class. This is, I would think maybe hopefully if I can get through all the things I want to get through today, the last in our series of lectures for right now, looking at shear force and bending moment diagrams. And what I want to do is I want to look at a cantilever beam problem, because I mentioned before I wanted to get to that and I wasn't able to get to that in the last lecture. But this is going to be a cantilever beam problem. Let me just get the numbers in. 1, 2, 5, 6.5. So somewhere around here might be good. 1, 2, 3, 4, 5, 6.5. There we go. I'm going to give us plenty of room, underneath it, so that we can draw the shear force and bending moment diagrams. Like I said, this is going to be a cantilever beam problem, so this is built into the side of a wall. Now, just 1 meter in to this, I'm going to have a 10 kilonewton force. And then another 1.5 meters, boy, I didn't do that right, did I? Another 1.5 meters, I'm going to have a 20 kilonewton force. And then I'm going to go another meter, which would be right here, and I'm going to have a uniformly distributed load all the way to the end of that cantilever beam. Does everybody see that? And this at the end is going to be 8 kilonewtons per meter. Now, what I want to do is I want to give you the actual distances here. I should probably have made that twice as big anyway, but you're always running out of room. So we want to actually look at that line as it comes down, at least into the shear force thing. And we want to look at this line as it comes down into the shear force diagram, if nothing else. We want to look at the very beginning of that distribution. We don't really have to look at things within the distribution, but want to look at the beginning and the end of the distribution. And so this right here is going to be 3 meters. This is 1 meter. This is 1.5 meters. And this is 1 meter. Does everybody see how that works out? And then let's say that this is going to be my shear force diagram. I'll put that down here. You're probably wondering, why did I put that down so far? And the reason for that is on a cantilever beam, just about all of the shear force is going to be positive, right? Because it has to be, because you have to be going up from a negative slope for the bending moment diagram up to 0, right? Because at this end, it's going to be 0. So let me put the bending moment diagram right here. All right, because this is going to be coming up from here, and this is going to be going across up here, right? So it's positive because the slope, right? Remember that the slope of a line, right, is positive. So the slope of something going up and to the right is positive, whereas the slope of something going down and to the right is negative, right? Everybody realizes that, right? So as I start to go up here, I'm going to have a positive slope, so I'm going to have positive this, because I'm really just integrating this into this, right? And in fact, we're integrating this into this. So let's see how that works out for us. All right, We've got to do some static equilibrium analysis first for this problem right here. We know that we're going to have a force R sub A, right, at that point, and we're also going to have a bending moment at that point of M, whatever M turns out to be, okay? All right, so the first thing that we want to do is we want to find out what R sub A is, and that's pretty good. R sub A, which is working up, is working against all these things working down. So I've got 10 kilonewtons plus 20 kilonewtons plus, and let's see, we've got 8 kilonewtons for 3 meters, so that's going to be 24 kilonewtons, right? So 54, 54 kilonewtons. So we know that R sub A is going to be 54 kilonewtons. Let's draw that. In fact, you know, I'm going to draw it with the blue pen. Let's see, 50, 1, 2, 3, 4. Can't go really 5, but I'm going to go up to about here. So that point right there is going to be, let's just mark it. That is going to be 54 kilonewtons. Everybody see that? This point right here. Then do we have any forces between that and that point there? No, no, we don't. So R sub A and this, it's just going to go over like that. Then it goes down 10, right? So I'm going to go down to 44, right? Does everyone see that? So I'm down now at 44. Then this right here, I should have written that different. That is your 20 kilonewtons, right? The next one at 1.5. So it's going to go down another 20. So I'm at 54, 44, 24. Okay, so this is 44. Nothing across there, so I could have actually labeled that. That is 24. And then at 24, you know, because nothing has gone across there, what about here? Now we go down, because what is that? That's 24 down, and that's going to occur. Now this is a constant, so if I integrate the constant, it's going to give me a straight line, isn't it? Right? So 24, and then it goes down to eventually at the end 0 kilonewtons, as it should. So my shear force diagram is this. But what's the one thing that you notice about it? It's all positive, isn't it? It's all positive, and it should be, because the slope that it represents, and in fact, there's going to be 3 different areas here too, isn't it? 1, 2, 3, 4. 1, 2, 3, 4, right? 1, 2, 3, 4. So different areas of slope. So we're going to have 4 different unique areas that we have to figure out the slope for, and then we're going to figure out what that means. And of course, it's a positive slope, isn't it? So it has to start back here, and then it's got to go that way. So we don't know what the slope is yet, but we can easily figure that out point to point, because the one thing we know with the cantilever beam is that M equals 0 at the free end. M equals 0 at the free end. So the first thing that we want to know is, well, where is it going? It's got to be positive, right, going up. And we know that it's going to go like this. The slope is going to be 0 at the end. So what is a 0 slope? A 0 slope is 0 slope equals horizontal, right? Rise over run. Whereas an infinite slope is going to equal vertical. So the slope is going to be horizontal at the end. It's going to be larger up here. We don't know how much larger, but it's going to go from 0, then it's going to go to a positive. So it's going to start positive, then it's going to go to 0. So let me do that. Let's say that it's a small positive, just like that, and it goes to 0. Right? Now, what is that value going to be right there? Let me mark that. What is this value? Oh, that wasn't very good. What is this value going to be right there? Because when we figure that value out, it's going to be great. And isn't it the area under the curve? Isn't it the area under the curve here? Let's see. I've got 3 meters. And then I start here with 24 and I go to 0. So 3 times 24 divided by 2, that'd be 3 times 12, that'd be 36, wouldn't it? So isn't that 36 kilonewton meters? Does everybody see? Of course, it would be minus 36 kilonewton meters. And then that is going to go down to 0. Now we can work our way back too, can't we? Because we know that that point right there is the slope of the line. We know the slope of the line is not going to change. So whatever the slope of this line was right here is going to become a straight line here, isn't it? So I've got that rounding there, and that slope is going to be a straight line there. The slope is going to be a little more angled there. So I've got this angling here, I've got this angling down, and then it's going to get even more angling, right? Because it's even going to be higher when it finally gets to whatever that maximum is. But we can figure out what that maximum is, right? We can figure out what that maximum is because we can do each one of these. This one is 24 times 1. So 24 and 36 gives me 60 minus 60 kilonewton meters. Does everybody see that? That's not a good pen. I'm going to have to get some more good pens. Now, we go to the next one. The next one is 1.5 times 44, so that's going to be 66. So this one right here, I probably shouldn't have drawn it that far away. This one right here is going to be minus 126 kilonewton meters. And then we're going to go back to this one, which is still another 54 kilonewtons times 1 meter. So 54 kilonewton meters added to that. And I have 50, just a second, 180 minus 180 kilonewton meters. And where would that occur? Of course, that would occur right at the base. And so where in the length of this is this going to be? Well, I'll tell you what, right here at the base, and this is what you would expect when you're jumping on a diving board. Where is the most torque being placed? It's being placed right there where it's hitched into the wall or whatever. And where, let me get the green pen, and where is the greatest shear stress? The greatest shear stress is right here within that first thing too. So that's where we really have to worry about a cantilever beam, breaking or whatever, is right at where it's attached to the wall, right? We're jumping up and down on this, it's a diving board, whatever. But that's what that's what we have. Let me just bring that down there. And we have all of the points. If I wanted to, there's another color. If I wanted to just crosshatch in what we've got here. I think I crosshatched this the wrong way now that I look at it. I should have cross-hatched it the other way, shouldn't I? But yeah, really. But that is going to be our bending moment diagram for the cantilever beam. Positive slope, and as you can see, all the way up here, we've always had positive slopes, haven't we? Always positive slopes all the way to the end, and of course, these are all positive. So it still works out exactly like we've always thought. This is how shear force and bending moment diagrams are put together. And when we can get the information off of these due to the distribution and loading and everything else, then we can tell exactly what's going on inside the actual beams that are holding up the floor or beams that are holding up the bridge or whatever. All right. Now I'm just going to put a line under this because we got our sub A. I want to put a couple other things here. So let's get V max equals 54 kilonewtons. And let's put M max. M max equals minus 180 kilonewton meters. All right. And so that's our problem that we did right there. Now I want to look at another problem. And what this problem does is it uses non-uniform loading, right? And when I mean non-uniform loading, it could be anything. I'm going to use a triangular loading, or I shouldn't say triangular, but an ever-increasing, loading, so that it's not too hard on the integration. But let me show you what I mean. I just have to get some numbers here. Let's see, 2, 3, 7, 10. Okay, so let's start over here. I think that's 10. I'm hoping, because if not, then I'm going to have to use my correct pen or something. There we go. Now, this is just going to be a simply supported beam, right? I'm going to try to make the loading more difficult. This is going to have a non-uniform distributed loading in it. So let me give you a couple of the distances and stuff that we've got here. So at 2 meters, I'm going to have a 10 kilonewton force. We're all familiar with that. And then 1 meter later, I'm going to start a distributed load. Just a second. I have a telephone call coming in. Hello, class. I'm sorry about that, but my brother called me up, and we got family business and things going on, so I had to grab that call. Now, this is 4 meters across, right? And that's our uniformly distributed load. But now I'm going to also put on a another load, and that load is going to be a non-uniformly distributed load. Does everybody see what I've got there? Oh, this is a relatively complicated, simply supported beam, isn't it? Now, I'm going to give you some information here. This is going to be 4 kilonewtons per meter. And this one up here is going to go from 0 kilonewtons per meter to a total of 12 kilonewtons per meter. Does everyone see that? Okay, so let's just drop our lines down for our shear force and bending moment diagram. Everybody sees what the distances are. That would be 2 meters. This is going to be our sub A and our sub B, right? And we're going to drop some other lines down here too, some construction lines for our shear force and bending moment diagrams. And this is also going to take into account the centroid for this triangle. Thank God we already looked at centroids, and we know the centroids for triangles and rectangles and everything else. So we can easily do this problem. So the first thing that we want to do, of course, just like always, is sum forces in the y direction. And what we're going to do is we're going to get r sub a plus r sub b minus, and then let's just do the whole thing, 10 kilonewtons, times, is that 5? Did I screw that up? Oh, no, that's right. Yep, sorry, I forgot to drop my construction line down there. That's 1, and then that is 4 meters. So that's 16 total, 16 kilonewtons total. And then this over here is 3 meters. So if it was a uniform, right, loading, if it was a uniform loading, that would be 36 kilonewtons, wouldn't it? But it's not. It's a triangular loading. So it's 1/2 that, isn't it? Right, I got 0 sandbags here and I've got 40 sandbags here. Right, so our peak, like I say, is 12, but what is the area of a triangle? Isn't it 1/2 a times b? So 3 times 12, 36 divided by 2 gives me 18. So I've got minus 10, minus 16, minus 18 kilonewtons. Well, I guess these are pluses then, aren't they, if I put parentheses around it? All right, so there we go. So actually what we get here is r sub a plus r sub b is going to equal 26, 36, 44 kilonewtons, right? Everybody see how I do that? Now, let's sum. We can do it with A or B. I like to do it with B, so summing the moments about B equal to 0. Well, we've got r sub A. That's going counterclockwise, so that's going to be a negative. So r sub A times, is that 9? Oh no, 10. I'm sorry, put that there. 10 times 10 meters. And that's a minus. And then plus 10 kilonewtons times 8 meters. I'm going to extend it over here, plus, now what do we do with this 16 kilonewtons? It's right at the centroid, right? So it's right in the center there is where we're going to put the 16 kilonewtons. Right in the center, right in the centroid. And so 16 kilonewtons, and then how far am I going? 3 plus 2, or 5. So I've got, yeah, I'm just looking at this for a second. Okay, so 16 kilonewtons, and then times, actually violates some of the way I usually do that. Take the anyway. I think everybody sees the positivity negativity of the moment, and so I'm just using the magnitudes here. And so that's going to be 5 meters. And then plus, now we've got to look at the centroid of the triangle, don't we? So the centroid of the triangle is going to be right here. And we're going to put the full 18 kilonewtons right at that point, right? So I've got 18 kilonewtons times 1 meter. Does everyone see why it's 1 meter and not 1.5 or anything? It's 1 meter because the centroid of this triangle is 1/3 of the way from the base, right? Just like the rectangle is 1/2 the way. So that's 5. So this becomes 1/3. So it becomes 1. And if we look at all of these, we can then figure out what r sub A is, and then figure out what r sub B is, and finish all of our bending moment and our shear force and bending moment calculations and diagrams, right? So let's do that. So I've got 80 plus 80 plus 18. So 178 kilonewton meters divided by 10 meters equals 17.8 kilonewtons. All right. All right, so R sub A is 17.8 kilonewtons. Boy, I've seen that someplace before. That was in another one of examples, came out to about the same. All right, so that means R sub B, right, because R sub A plus R sub B is 44. So 44, I'll just do that. 44 minus 17.8 gives me 26.2. So 26.2 kilonewtons. R sub A, R sub B. We can now put our shear force and bending moment things together, right? So I'm just going to draw my shear force across here. There we go. And how do we start that? Well, the first thing is we're going to go with R sub A, and R sub A is 17.8 newtons. So let's say that this would be R sub A going up, right? Do we have anything from R sub A going over? No, we don't. So we go straight across there. Now we come down 10. So 17.8 minus 10 is going to give me 7.8, right? So we're at 7.8 now. I'm just going to write 7.8 in there. Then we go across, and then I'm going to go down 16. So 7.8 minus 16. Probably saying, hey, this does sort of look a lot like no. But anyway, but now we're going down 16 because the other time we were going down, I think it was 15 or whatever, but this is 16. So 7.8 minus 16 is minus 8.2. So now I'm over here and I'm at minus 8.2. And how did I get there? Right, this is a constant. So I'm going to have, let me just use my ruler, my beautiful transparent ruler. Yeah, they should only make rulers transparent. I've used that's aspect of it so many times. Like when you're trying to hide a ruler. Now that's going down to minus 8.2 kilonewtons. If we can write kilonewtons, let's do it. Now, how does it go from there down to there, right? Well, you're probably saying, well, okay, this goes down to here, but then this is going to fall off. I'm still going to have whatever that is, but then this is going to fall off parabolically, isn't it? Because look at the slope. The slope will start right at the same, slope as this, right? Or it'll start at 0, I should say, because it's at 0. So the slope is going to go from 0, and then it's going to go to a higher positive number. Is it going to go vertical? Is that infinity? No, it's not infinity. So it's going to go to a maximum of 12 kilonewton meters per meter, right? So it's not going to infinity, but it is going to look like this, right? Because it's parabolic. So it keeps this, but then it falls down there. Actually, no, that's not true. Let me get my correcto type here. I don't think that it does that. I think it does this. Yeah, that's how it goes. Now I got correct type on here. It's probably ruined my pen. The pen was about to be ruined anyway. There you go. That's how it goes. I'm sorry. Because it starts at 0, and 0 is horizontal, right? So right at that point, it's going to start at 0, and then it's going to go down to a positive. It's not going to infinity. It actually is going to hit that at some type of finite slope. All right? Now, you're probably saying, well, how in the world with something like this, how are we going to figure out what the area under the curve is, right? For our bending moment diagram, which we're certainly going to have to put in. I'm going to try to save this pen, even though it has correct type on it now. I'm going to write the correct type off while we do this. So this is our, I'll put that back on for a second. This is our shear force diagram. And I think you can see how I'm going to find out what the maximum is there, right? That's right. Because you can see that on the left-hand side of this, I'll just call this my my bending moment diagram down here and give you as much room as possible, right, to see it. Okay, so first of all, it's positive. That's positive, and we know what that value is. That value is 17.8. 17.8 newtons. So 17.8 newtons times 2. 17.8 times 2 is 35.6. I knew it was. I just thought I'd, give you guys a chance to do that. Okay, 35.6. I'm going to draw it like this. Fairly high, right? So we know that that point right there, let me even get a better pen, is going to be 35.6 kilonewton meters, right? Okay, now the next one is relatively smaller, so we're going to just draw it like that. And now that's 7.8. So 35.6 plus 7.8 gives me 43.4. I'm going to use a brand new pen. 43.4, right? And that is that location right there. Brand new pen. 35.6 is right there. And 43.4 kilonewton meters is right there. Now we go down to 0, don't we? In fact, we know where we're going to get to 0. We're going to get to 0 right at this point. So it's going to continue that direction, and then it's going to flatten over towards 0 right at that point. And where is that point? This is 16, 8.2, 7.8. It's not right in the middle, is it? In fact, what is this distance right here? And then we'll also know what this distance right here is too, won't we? Right? So it's 7.8 out of 16. So 7.8 divided by 16 times 4, 1.95. So this distance is 1.95 meters, and this distance is 2.05 meters. Does everyone see how I did that, how I extrapolated the center of that? And of course, that allows us to find out what this value is, because I've got 1.95 by 7.8 divided by 2. Let's just do that. 7.8 times 1.95 divided by 2 equals 7.61. So 7.61 plus this, well, let's, I'm going to do this. Area equals 7.61, right? Just so that you know that the 7.61, that's how it got there. So the 43.4 plus that 7.61 gives me 51 even. 51 kilonewton meters is going to be that's a 51, right? I'm going to circle that. In fact, why don't I just write it here? So M max. I'll go back to using the horrible ones. M max equals 51 kilonewton meters. So we've got R sub A, R sub B, M max now. We also want V max. V max, we have that right above, right? So, because we know that R sub B is 26.2, so we know that that has to go back up 26.2, right? Where's our maximum? Our maximum is here, minus 26.2 kilonewtons. So when we find V max, it's going to be minus 26.2 kilonewtons, right? So now we know all of our things. We know V max, so we can figure out what our shear stress is. Where is our maximum shear stress? We usually do that in green, don't we? So our maximum shear stress now is going to be right here. It's a single point right here is where minus 26.2 is, right? So right there is where our maximum shear point is going to occur. It's not a region anymore, it's just a point. How about our maximum bending moment? Well, we haven't even finished our bending moment yet. We've got to 51 kilonewtons. Now we're going to have to subtract this off, don't we? So we've got to subtract 2.05. So 51 kilonewtons minus 2.05 times 8.2 is 34.19, right? So, well, did I say 51? Oh, excuse me. I forgot to divide it by 2. 8.2 times 2.05 divided by 2. And then 51 minus that gives me 42.6. So we want to come back down, and this is going to be in a parabolic spandrel. We come back down, and that location right there, I've got to use my small pen again, my new pen. That location right there is 42.6 kilonewton meters. Does everyone see that? So that's pretty good. Now we can actually see how this is going to go. We're going to start with that slope, but then the slope is going to get much more negative, isn't it? In fact, the slope is going to go way down like that. So it's going to come out here, and then it's going to go way down like that. And we know all of our various moments all along there. All right. Okay, I think we're going to hold it there. The timer went off. I know I've got a little more space down here. I didn't really have anything else planned. I just didn't use as much space as I thought I was going to use. I do have another example problem here, but I think I'm going to let that go. And I think that we're up to around the time anyway. So I see you at the next lecture.